In this video, we'll describe the type of diffraction pattern, the interference pattern you get from a single slit. Yes, you heard me right. I said a single slit. The first thing you might think is, wait. Why would a single slit have interference? Because doesn't a single interference have to do with multiple light sources overlapping? That was the whole thing with the two different wave machines. If you just had one wave machine, you didn't have this whole still moving whole thing. So wait, what's going on here? The other thing you might say is, wait, why would you leave this till the end? And I'll answer both these questions in a little bit when I explain what's going on. So let's first have to show you what you have here in front of you, what it looks like if you shine a laser light through a single slit. Well, what you get, to be precise, is a very large central maximum that's significantly wider than the maximum you see on the others. And the maximum off to the sides are significantly dimmer than the maximums from the two slit. The two slit pattern, which looks like kind of like the 3 slit and the 4 slit and the 5 slit and so on, were basically just the same. Basically the same brightness, one after the next. So we have clearly bright spots and dark spots caused here, but they're in a slightly different pattern. And what we're going to try to do is explain this whole phenomena. And the way we're going to start this is just by discussing, wait, where are the multiple sources that are coming together to cause interference? Because to have interference, you need at least 2 wave sources, if not more. Okay, so I'm going to draw a single slit. And I'm going to draw a zoomed in version. So here's the blocky material. Here's the other end of the slit. You have the blocking material. Maybe it's, a piece of plastic or metal or whatever it is. And I'm going to imagine a wave front coming in. So these are like the same sort of wavefronts we have. These are the wavefronts of light. And I'm going to imagine a wavefront is passing through here right at this very moment. Well, what I'm going to use is Huygens principle. And if you remember, Huygens principle says that we can replace every single spot here with spherical wavelets. And when I draw this, I keep drawing little teeny wavelengths like they're really close together. They're not really close together. They're just evenly spaced with these So this space should be the spacing here between 2 wavefronts should be the same as there, which would be the same as between here. I'm just not very good at drawing it. But every single spot here is going to act like it's the source of a spherical wave, which is, in other words, to say every single spot along here acts like a slit. So here's maybe another way of visualizing this is if I took this as a solid piece of material and I cut a teeny little bitty hole in here, I'd have 1 slit. And if I cut another teeny bitty hole in there, I'd have 2 slits. And another one, I'd have 3 slits and 4 slits and 5 slits. And I would cut it down so every single point I remove the material, I would have an infinite number of slits, or in other words, 1 fat slit. Okay? So an infinite number of thin slits, slits, equals 1 fat slit. So if we talk about a slit of some width, and notice before we never talk about the width of a slit because we assumed it was so small that all the light was coming from basically 1 spot and it didn't matter. But here we'll talk about cases where that's not true, and we'll call the width of the slit A. then that'll act like an infinite number of slits spread out, wave sources spread out like that. So the single slit case is like the infinite slit case. So that's why it appeared after the many slit case. We went 1, 2 slits, 3 slits, lots of slits, many, many, many slits, like hundreds of slits for diffraction grading, and now an infinite number of slits. So how do you possibly figure out what type of interference you have from basically an infinite number of slits? Well, I will try to go through a diagram that will help this make sense. Well, here's how you do this. If you want to talk about how much further ahead the waves are, well, let me back a step up. Each of these waves are going to add their own displacement. And I'm going to talk a little bit in college physics 1, chapter 13, language. Displacement meaning what is different that makes this a wave. So for light, it's the electric field or magnetic field. For water, it's the height of the water being higher or lower. For sound waves, it's the displacement of physical material or the pressure being higher or lower. That if you have several different sources, they just add all their displacements up. That's what we said when one water wave raised you 1 meter up and the other one raised you another meter up. Also, that the function for what those displacements are were sine waves. It was like each of these is amplitude sine 2 pi t over the period, really minus 2 pi x over the wavelength. And there can be a little extra bit in here, but the point I want to have is these are sine functions. And then if I find the total, that's just going to be adding up the displacement from each individual. So he's source 1, source 2, source 3, so on. There's an infinite number of these. And if you remember from back when we did RLC circuits, there's a tricky way of showing sine functions. And that's to use circles or in vectors. So I'm going to draw a circle. Here's the center of the circle. And a triangle in my circle. That right there is a sine function of that angle. And if I want to imagine adding up lots of sine functions, the easiest way to do it is to imagine a lot of dots, locations, along the center of the circle, or better yet, imagining a bunch of vectors that went out like this. And then you just add all the vectors together, and then you then see what the y component is overall. Okay, so what I'm going to do is draw the location of the tips of these arrows from all of these sources. And you can think about these arrows here, which I will omit drawing, I'll just draw the tips, as being like it's pulling in one direction. So, for example, and let's interpret this, by the way. So these dots over time are going to go clockwise, counterclockwise around here. This is just wave discussion back from chapter 13. So that the starts out with sine of 0, so it's 0 displacement. It gets up to the top at and that's at maximum, and then it's at the bottom, and then it's going in the middle, 0 displacement going downwards, and then it's at the bottom, it's at a trough, and so on, and it repeats the cycle. Some point, say over here, which is equally distant to all of these dots, so you can take up any pair and say that they're the same distance there. All of the dots, and especially if it's very far away, any extra distance because it's basically every dot is the same spot distance from x. It's not quite true on this triangle, but if I drew this more exaggeratedly, you'd see that's basically true. So all of the different sources would be up here, say at a maximum at one time, and then at a minimum going to zero, or to zero going down to the bottom, and then at a minimum, and then at zero going upwards. And you can be like, it's a bunch of arrows that all go up together. And since they're all doing the same thing at the same time, that's constructive interference. They all are in sync with each other. But now let's imagine just the sources on the very top and the sources on the bottom of the slit. And so this right here, this is x bottom, and this is x top.